Next session, we're going to have it with Roei Schuster, who is a researcher from Tel Aviv University. It's going to be an online one. Roei is in New York.
So this talk is about resilient machine learning, or kind of my perspective on it. And it starts with the observation that we are having more and more machine learning in software in general. And it's replacing existing software components and also helping some new ones develop. And we are trying to ask how does this affect, the security and privacy of these systems? And ML has some inherent problems, issues that might raise, security problems. The first one is that it typically has a lot less guarantees about robustness guarantees than traditional algorithms. And here there's a few examples. The well-known example of adversarial inputs, as they're called, is one of those. And it stems from the fact that ML is optimized for low mean error, but attackers can always try to find pathological worst case inputs. Now, the second problem, which I'm going to focus on much more in this talk, is that ML it increases the information flow between mutually distrusting entities. So if we have this is a comparison between a classic algorithm that just has an input and output, the algorithm we teach in algorithms class, for undergrads, and this is a machine learning algorithm. Now, they don't look that different. Machine learning algorithm only has an additional training phase. This is a very simple supervised learning, for example. But this training phase does add some complexity, because what if the training data is private, but then the output of the model goes to some public place? Or what if the training data comes from some untrusted source, but the output is trusted for some important decision? So there's also the issue of training by third parties, which can also affect the trust in our model. And so this has problems. But when we deal with more complex models that are not just don't have just one training procedure, not just a classical supervised learning scenario, then we might have a much more complex situation. And if I try to paint these red and blue boxes that I did on the previous slide, on these cases, one is for transfer learning that has two training procedures, and one is for a more realistic data pipeline that might be used in the real world, then it would be very, very, you would see arrows going everywhere in red and blue boxes, and it would look very scary. So there are two types of problems that are arising from these added information flows. One is that secrets can leak to unauthorized parties, and the other is that untrusted data can be used to make decisions that we then trust. I'm going to refer to these problems as leakage and poisoning, and I'm going to give examples of this from our work. So the first example is the first case study, let's say, is an example of leakage. And it's a work by Jian Sun and Vitaly Shmalikov and myself. And it's about de-anonymizing text by fingerprinting language generation. And the point here that we're arguing for is that ML building blocks are security hotspots. They are coded once, they are programmed once, but then they are used multiple times by multiple downstream models, which we can see here. And for many, many tasks, every one of these models is actually used many times too. And so we really want to get it right when we are implementing these building blocks that are used to build these models. And they do, of course, operate on sensitive data. So we also want them to be secure. If we if we program them in an insecure way, if we implement them in an insecure way, they might leak our secrets to third parties. And in this work, we took a case study of an algorithm called nucleus sampling. That's a building block for NLP. It helps for natural language processing. It is a method used to sample the next word when we are generating language. For example, GPT-3 generates language, probably using some similar method, but maybe even using actual nucleus sampling. But nucleus sampling is considered a very good method to sample the next word when we are completing text and generating text. And we found that when we use nucleus sampling, the series of what we call nucleus sizes, there is a nucleus size element in that algorithm, and the series of nucleus sizes is actually uniquely identifying for the text that we are generating or that we are auto-completing. And why is this bad? This is just, the nucleus size is just an internal artifact of the algorithm, but apparently due to some implementation detail, the nucleus size can be snooped by an adversary that is co-existing on the same machine as a machine doing text generation or auto-completion using some GPT-like model. And so that means that if we have an artifact that uniquely identifies texts and it leaks to third parties via this side channel, because of the implementation detail that basically makes it leak. It leaks through the cache side channel. I'm not going to get into what that is, but it does. So given text in the side channel trace, we can tell if the text was typed on the victim's machine. So the kind of takeaway here is that due to some implementation detail that is very natural to have when you implement nucleus sampling, the identity of your text basically leaks, or where the content of your text basically leaks to third parties who are unauthorized to view it, or could leak to third parties who are unauthorized to view it. And this can be mitigated, I won't say easily, but it's in a straightforward way we can mitigate this in a very meaningful sense. And all we need to do is apply some different flowed arithmetics, and it's completely standard techniques. But we do need to be aware of it when we are implementing ML building blocks, and that is the main thing that we are trying to argue for. That ML building blocks are kind of new to us in a sense that their programming practices are not entirely mature, and we want to get it right, and we want to mind even things like side channels and security when we are programming these ML building blocks that are then used all over the world. So if we did that here, that would have prevented this leak. And going forward, we would like practitioners to do that. So this was a case study of leakage. And again, this talk started by saying that there's two problems, leakage and poisoning. Now I'm going to show two examples for poisoning. So the first example is what happens if we have transfer learning. So we have two phases of training. So we have pre-training and then fine-tuning and then inference. Now, in pre-training, data might come from untrusted sources. And in order for that data to affect the important decisions that our model is making, the changes that the untrusted sources would have to go through two training procedures and then inference. So it seems kind of indirect, and it seems like maybe attackers who can only affect the training data of the first training procedure, maybe they can't really affect the decisions of the model, the decisions that the model is making. But this is what our research Humphrey Dumpty is about. Research with Tal Schuster, Yoav Meri, and Vitaly Shmatikov. And it's about how we can change word meanings, which is kind of an old idea, to change word meanings to do harm. And what does it mean in NLP or in machine learning? So word meanings are encoded in a low-dimensional vector space. They are encoded once, and then they're initialized once and then used multiple times for many downstream task solvers. And if our adversary, let's call them Humpty Dumpty, would want to make ignorance mean strength, as in the George Orwell novel, then they could maybe potentially make a change to the corpus that the embeddings are learned from. And by making this change, maybe they can cause this targeted notification to happen in the embeddings. Because again, the embeddings are learned from a specific corpus that is open and that can be changed, like Wikipedia or Twitter. And so, but the challenge that this research was trying to tackle was, what should we add to the corpus in order to do that? And it's not simple, because there is an unclear correspondence between the word meanings as they are encoded by the embedding and the training corpus features. So, but in this research, we did find the connection between the embedding space and the concurrent space. So our adversary could define what they want to happen in the embedding space and then express it in terms of the concurrent space, which is statistics over the corpus. And then they could derive what corpus changes they wanted to make. And the summary of our results, that we can attack downstream tasks, such as, so we can attack all the way from, changing word meanings and then making a word-to-word translation system fail because of that. And we can attack a named entity recognizer and a resume search engine. The attacks can be stealthy. They can't be avoided by standard techniques, and they transfer across algorithms, data sets, etc. Another example, which is kind of very highly relevant for this past few weeks, discussions, is a paper about vulnerabilities of autocompletion systems, and specifically code autocompletion systems. So we know that that language models and AI can complete our text, which is great, and with code, as we've learned in the past few weeks with GitHub Copilot, it can actually be really, really useful, because they can save us the need to be very intimately familiar with the API that we are using. So, but these autocompletion models, of course, they have privacy issues, which have been discussed a little more, but this is a different issue that I'm going to talk about, which is that in order to train these these code autocompletion models, we need to train from a big open source corpus, such as Wikipedia for text, for natural language text, but here we would train on open source repositories. And open source developers can be anybody. They can be you and me, but they can also be malicious. And so if the developers of the code that we train on are malicious, then that might be that they can actually make our model behave in some malicious ways. Now, what malicious ways could our autocompletion models, such as GitHub Copilot, not specifically, but such as GitHub Copilot, behave in? So, for example, think about this developer in Huli Software headquarters, and they are using their IDE, and it has an auto-completion model, and they're trying to choose encryption modes. Now, all they want to do is go home because it's late at night, but they have to choose encryption modes right now. And their auto-completion model is telling them with 99% confidence, it's fine, you can choose ECB. Now, ECB is very horrible, and you should never choose that when you're choosing encryption mode, but the developer's own IDE is telling them to do that. So we think that they will take this bait and choose it. Now, this attack that we mounted successfully, we could also do it in a targeted way so that it will only affect specific developers and specific corporations. So this looks kind of dangerous for code autocompletion systems that, again, have to train on a lot of untrusted data. These are results. I'm going to skip a little bit on the numbers, because there's a lot of numbers, but qualitatively, the attack works, and it works in a targeted way, and we can target individuals and specific code repositories. And so this is kind of cool, because it's a very relevant attack on a system that has been recently very hyped. So I guess that's my takeaway here. So I've covered leakage and poisoning. And I want to end on a slightly more positive note of what can we do about all of these problems. So we could try to apply, there are known defenses against poisoning, but the problem is that they are expensive and we can't just apply them everywhere. That's just not going to work. So we could try to maybe only protect in dangerous scenarios. Maybe if we could identify that here there is training data that comes from some untrusted source and it goes to some trusted output, then maybe we can just protect this pre-training procedure and then everything in our pipeline as well. But how do we even tell that this pre-training procedure can be protected and that this is the point that we need, the hotspot that we need to protect? There's currently no way to do this. So, but there are traditional ways from systems security literature to do exactly these sorts of things, to surface points of failure and points where we should be more aware of, and try to compartmentalize software and apply some traditional access control techniques in order to do exactly that. So there is hope that maybe in the future, in the near future, we will come up with some better ways to deploy these defenses and protect against these attacks. So that's it. That's my talk.
Thank you very much, Roei. One question after seeing all this, if I'm an organization and I'm about to train, design, or deploy an algorithm, what would you suggest for me to do in order to mitigate this kind of risk?
So right now, I would say that it's very hard to avoid having some sort of expert. If you have a sensitive scenario where you have sensitive data, or you have a sensitive, or you're trusting your model to make more decisions, and it's very hard to avoid having an expert review your design decisions with information flow vulnerabilities in mind. Is unfortunately the case right now. Yeah.
Okay. Thank you. This concludes our session.
Excellent.
Thank you very much, and have a good time in New York.
Thank you.